So, how do microcontrollers talk to devices at lightning speed? Meet SPI. It's fast, synchronous, and it can send and receive data at the same time. First, using code to pin in this video, we'll break down exactly how it works, and we'll get under the hood with simple raw code to master the hardware basics. Second, we'll see how using libraries makes the task incredibly easy with practical coding examples. Ready to master SPI? Let's dive in. We have a breadboard here. We've got an Arduino Nano, which I'm going to plug in here across the gully. We've got a BMP 280, and if I just spin that up onto the side there, you can see it says it BMP 280. And it's very small actually. If I turn it around, you'll be able to see the chip. So this is a temperature sensor, a barometric pressure sensor, and by extension, elevation detector. You can see how small that is. In the data manual, it looks absolutely massive, but in reality, very, very small. And it's terminated on the edge connectors there. You can see you've got the VCC, which is plus 5 volts, ground, serial clock, SDA, chip select bar, and the SDO. So I'm just going to plug that in there. What I'm going to do now is I'm going to start wiring it up. So we've got 5 volts there available to us coming out of the Arduino Nano, and we'll just plug that into the 5 volt line at the bottom. So that will be our distribution. Push that in. We need to get the 0 volts, which is 2 pins away, which is on there. I'll put that in. Now we need to pair the plus sides on the top to the plus side on the bottom. So we've got distribution of our power. So there's that. And we do the same for the 0 volts. The power is going to be coming through the USB connector here. Now what we need to do is connect up the power into the little sensor. That's connected in now. Now we need to complete the wiring shown on the diagram. So we've clearly got the pins marked SCK, MOSI, MISO, chip select bar. But let's just put the cables in. So we'll go from 10. Right, so the chip select on pin 10 there. And that will go to the chip select bar on here. And then 11 will go to SDA. So that's the serial data in from here. And the next one will go to pin 12 to SDO. And then finally we've got pin 13 to connect in, and pin 13 is going to be our serial clock. So we'll tuck that underneath there. We'll put it into the serial clock. I believe that's correct, but let's not take anything for granted. Let's just make sure that everything is actually what it's supposed to be. So if I put my meter onto continuity, so let's start from 13 is serial clock, and that goes to the serial clock there. Let's go from pin 12. Pin 12 is our MISO, and that goes to SDO, which it does. Pin 11 goes to SDA, which is that one, and pin 10 needs to go to chip select bar, which is that one. Make sure that that's connected there and the ground is connected there. So we've got a little switch here. When we get to the code, we're going to be using this to trigger the events that we want to see on the screen. I'm going to put the ground in there and just plug this in to D7, which is there. We've got a trigger switch now, or a go switch. So let's upload some code into the Nano. So I'm going to plug it in. You'll see it light up when I power up the port. Bingo bongo, we have power. We're in the Arduino IDE 2.3.9, and this is a small program called BMP280-test, and all it does is to use a technique called bit banging. So it's a very simple program. At the top of the page you can see we've got the definition of the pins which are related to the communication from the Nano to the BMP280. And so we set these defines up with user-friendly names that we can easily see and understand, and assign them a number. So we've also got the start button going into pin 7, and the command, which is command read ID with the value XD0. Two little methods there. One is to set up the mode of the pins. So this is an input, but it's got a pull up on it as well. So for the start button, it means that it has an internal resistor going up to the 5 volts. You can ground that pin and get a 0, and that will kick off our interaction with the BMP280. The initial states for the pins will be set during setup. So we'll set the CSB high and we'll set these two low, which is the serial clock and the MOSI. So transact is the actual transaction that takes place, but we'll come back to that in a minute. So if we go to setup, we're in a serial monitor there, which we got to by going to tools, serial monitor, and you can see that the baud rate there matches the baud rate here. So we'll say serial begin at 9600, and we'll see it coming out on here. This is just waiting for this to have happened. Then we set that pin setup, and then we do the initial states. So that deals with that. Now we've got a very simple operation loop which says, it looks for the button, it says have you been pressed. If it has been pressed, it will continue forward. It will hit this delay, and the delay is there to stop any bounce on the contacts on the switch. And then we run a report, but we haven't got anything to report at this time, so we have to call transact. And transact being the method that we're going to use to talk to the BMP280 and look for what it's sending back. Once we've assembled that information, we will return that to report, and report will report on it. That will become very clear in a minute. You can see that report here is having that value returned to it by transact. And this is where the magic happens. First thing that we'll want to do is set the CSB low, so that tells the device that this is in SPI mode and it should be ready to receive transactions. So in our first loop, we're going to deal with sending the command. The command will be the D0 that I referred to. So this will have 8 transactions. It will be 0 to 7. So X will increment by 1 from 0 to 1 and so forth until it reaches 7. And it does that by determining at any point in this loop what the value of B should be. So B will either be a 1 or a 0. So what we're saying is we'll take the command ID and we will rotate it left, and that will be by X bits. So if it's 0, it won't rotate at all. And then, so for the first one, we'll have whatever the value is in command read ID, and then we will AND it with 0x80. So we're taking the most significant bit. And if that result is something greater than 0, then it's going to be a 1 or it's going to be a 0. So for those of you who don't really do much in the way of sort of binary operations when you're doing your coding, I thought doing a small animation might crystallize this particular line and what it's doing. It's a little animation using an HTML page. We've got the 080 there showing you 1 byte and the most significant bit set. And for D0, which is the command we're sending off to the little sensor to get its ID, we've got D0, basically 1101 and 4 zeros. Now what we'll be doing on the first pass is to AND that bit and that bit, and that sounds exactly what it is. So if that bit is 1 and that bit is 1, then the output will be 1 here. Then we will shift this left so that we're working on the next bit. We'll repeat the same operation, and the result will go in here and then here and here until we fill this up. That's exactly how it works. So let's see. If we press the button to start it, we've ended that with that. This is the target cell and it's a 1. If I step again, it's also a 1. The next one will be a 0. And the next one will be a 1 because that's going to move to there. And then all the remainder will be zeros. And that's the wave, that's the MOSI wave that we get out of here. So that's what it looks like. So if you're at all confused, hopefully now you are not. Right, and that's the bit banging part of it. So we've got the bit that we need, right, and then we put it on the line, the MOSI line, and then we set the serial clock high, wait a little bit, set it low again, then wait a little bit, and then we do it all again. And that is as simple as that. So the delays that we've got there are really for aesthetics more than anything else, because there is enough delay in running these commands anyway, and it makes it easier to see on the scope, which you'll see later. And we've got a nice little 2 microsecond delay there. The next thing we do is to go and read everything that comes back. But before we do that, you have to remember that when we're sending a command out, it activates on the leading edge, which happens to be a positive going edge in this case, and it's ending on a low. Though when we're on the first 7 iterations, we are not doing anything on that trailing edge. Nothing's happening, except for the very last one. So on the very last one, that's when it starts to try to send stuff back. So we'll have finished that. I will go in here. So we know we only need 7 transactions. We only need 7 more low going transitions because we've already got 1 here. Right, which means we can immediately go in and read that, what's on that meso, and then set the clock back high again, have a delay and go around the loop and keep going around until we get all the bits in and assembled into the chip ID, which is using a similar mechanism that we used above. It's basically shifting the bits along. So we build it up this chip ID, and we've done it then. We've got a chip ID, right? So then we close down the session here with a CSP goes high, set these back to low again, and we return the chip ID to the report. And in the report method, just formats this so it looks nice. This will come out and it will tell us what the chip ID is in hexadecimal, and then it will give us the binary equivalent as well. So that makes it nice to look at. What I'm going to do now is just press the button. If I press the button, report, chip ID equals 58, which we know it to be the case, and then we got the binary equivalent, and the binary equivalent of that is not an 8. That's a 4, then we have a 0, then we have a 1, so that's 5 in total on that left nibble, if you like, the first 4 bits there, and then the other one is an 8. So that's how we get our 58, and it is indeed the right address. No, this is not the end of the video, so please keep on watching, there's more stuff to come. If you are getting value from this video, please do hit the like button, because it inspires me to make more. And if you want to keep mastering topics like this, do hit subscribe so you don't miss the next video. Right, so I've got my scope in Logic Analyzer mode, and I've got D0, D1 and D2 probes set up to look at the serial clock and the MOSI and MESO lines. So I'm going to press the trigger switch now and let's see what happens. And there it is. Okay, so let's talk about the timing now. Let's just refresh our memory. This is the nano on this side, and this is the BMP 280 on the other side of these signals. So we're generating the clock, but we're only generating it once we've set the MOSI signal to the right level. So in this case, we're going to be sending a D0, and that's why we're clocking on the leading edge a 1, a 1, 0, and a 1. It says 1, 1, 0, 1, which is a D0, because the rest of them are all zeros. So we covered sending the D0 out on the pulses and how that works on the leading edge. What about the data coming back on the meso line? So it's from the BMP this direction. If you remember, I said the last negative going pulse, or the last trailing edge I should say, is going to be where the first data comes out here. Well, it did come out there, but it came out as 0. If we fast forward up here, because this is an artificial gap here caused by the program, on this trailing edge we get a 1, on this trailing edge we get a 0, on that trailing edge we get a 1, and on that trailing edge we get a 1, and all the rest of them 0. So that's going to be 0, 1, 0, 1, which is 5, and then 8, and then 0, 0, 0. So that's our 58 coming back, and it's really that simple, and that's what this bit banging is all about. Brutal code. Right, so hopefully that explains crystal clear how the data is transferred on SPI. Just as a point of note, we're using bit banging in this example purely for educational purposes. When the controller's got dedicated hardware in it to handle those pins, you wouldn't use bit banging. We're going to talk about SPI, polarity and phase and what that means. So everything we've done so far has been done in mode 0. So what is mode 0? Well, if we have a look over here where mode 0 is, you will remember that the serial clock starts low and it goes high when it's active. So on the leading edge we do something, and on the trailing edge we may do something. So we've got MOSI, that's the master out, slave in, going in this direction, and the MISO, master in, slave out, going in that direction from the device back to the controller. So if you remember from the Big Bang in, when we encountered a leading edge on the pulse, in this case it happens to be positive going, that's when we're clocking the data into the slave. And if there's anything to come back from the slave, it will be coming back on the trailing edge, which in this case happens to be negative going. So here we've got something called the phase. So that's what I was just describing to you. So the polarity is literally in which direction is it going when it's active. So if it starts low and goes high, that's a polarity of 0. For the phase on 0, that's exactly what I just explained to you. On the leading edge, we can clock in stuff into the slave, and on the trailing edge, we're reading the data coming back from the slave. So that's mode 0, but there are 4 in total, so 0 to 3. So for mode 1, we're still with a polarity of 0, so it's an upgoing pulse, it's a positive going pulse. But the phase is swapped, which means what we were doing on that leading edge and that trailing edge, we've swapped them around. So we'll be clocking stuff out on the trailing edge and the other way around for stuff coming back in. And then we've got, again, the 2 different phases which we just explained, but the opposite for the polarity. So the polarity is now 1, which means it's inverted. So we're starting high and going low, and the same for this one. So we've explained the phase, we spoke about the leading and the trailing edge, and the polarity of the serial clock, which all of these are serial clock, and I forgot to write it in there. Now, it's a guess that there's a tiny percentage which use mixed modes 1 and 2. So I'm going to say 5%, but I don't really know the figure, and that the majority, in fact, I've never seen so far any devices that use mode 1 or mode 2, but I'm sure somebody out there has, and they'll tell me I'm wrong. If that's the case, that's fine. I don't mind being corrected. So hopefully that explains how the modes work on SPI. It is the slave that determines what it will accept in terms of the modes that it can work under. As we did everything in mode 0, we didn't really have to do anything, right? Because the BMP280 will accept mode 0 without doing anything. So hopefully that will have given you a grounding in SPI and how the modes work. So now we're going to take a look at how we can use libraries to make our lives much easier. Have you seen the bit banging stuff now? We're going to do it differently. We're going to use libraries provided. So you can see in the top left hand corner of the IDE for the Arduino, we've got BMP280 library test.ino, and that's the script that I've put in here. So the start of it's very much the same. We are setting up the pins, but you'll see we've added a library. So there we've got the include add fruit BMP280, and that's all you need to put in there as a library. So we define the pins just the way that we did before, but now we're instantiating a class object. So we're going to create this add fruit class BMP, and in it as parameters we're going to put these pin numbers. So that tells the class how to work with the pin numbers. In the setup, it's similar to before. We do a serial begin, and now we're waiting for the BMP to begin. That's the sensor itself. If it doesn't, then we say, well, there's an error, check your wiring, because maybe you made a mistake, and it will just wait. Then what we do is we've got our switch there. We're going to look and see if that switch has been pressed, so that the input on pin 7 has gone to 0. If it has, then continue basically, and we come into the loop. So the loop is exceptionally simple. This is how much more simple it is to use the libraries, because it's all done for you. So this sensor, the BMP280, it can test temperature, it can test barometric pressure, and we can also calculate the elevation based on sea level. So in this, we're not going to be doing altitude, but we're going to be doing the barometric pressure. This is expressed in pascals, which is just one way to express it, but there are other things that you can do to create a calculated value for the other kinds of things like inches of mercury and so on. And then, of course, we've got the temperature, and it's going to be by default in degrees centigrade. You know how to convert that to Fahrenheit if you really wanted to. So in our loop, all we do basically is saying, right, okay, float temperature, and we read temperature from the BMP class. It's as simple as that. And then we go and print it. Temperature equals what the temperature is, and then C, centigrade. Same thing for pressure. Pressure equals, we give the number, and then we delay by 1 second, and then we do it all over again. So the first thing we're going to do is we're going to load it down, and you should see these lights starting to blink there. We're at 9600 baud on the serial monitor, which you, if you remember, you get to by going there. So we have that set up to 9600, that set up to 9600, and we should be ready to go. And all we've done is change the code. So let's put it to the Arduino Nano. Let's post it up there and upload it. So it's uploaded. Currently we've got nothing on the monitor because we haven't pressed the button. It's waiting at this point here. The reason I did that was so that I could explain this code before we go and look at what's happening here. So let's push that up a little bit, and then you can see I'm going to go and press the button, and it will instantly start to give us the temperature. As you can see, it's quite hot today. It's 29.3 inside. It's probably slightly hotter outside. We've got a barometric pressure in pascals of 102,083 or 85. Because this is on the bench and it's plugged in, I can't really start elevating it to show you the difference in the barometric pressure. But what I'll do is put my finger on it, and we can see and watch how this temperature variance changes. Now this is the back of the board here, so the sensor's on the other side, but it should sense the temperature change if I put my finger on the back. So we're at 29.5, we're up to 30, 31.567. Will we get up to 31? We probably will. And it will probably keep rising even further. I don't know what temperature I am, but it's still slowly rising. Yeah, that's probably hit its maximum at the moment. And that will start to drop again. So this proves the point that it's very simple with a library, but you've also done the hard work in the bit banging. Well, I hope you enjoyed the video and got something out of it. And if you did, don't forget to like and subscribe. And I will see you next time.